All right, guys, I have to stop this here. I can see that this is a really interesting and fun presentation, and thanks for all the good Q&A.
Thank you.
So our next presentation will be on Thanos, programmable multidimensional table filters for line rate network function. And actually, Vishal will be here twice in a row, or both on a single author paper. And Vishal is as such really successful here because single author papers aren't really happening at SIGCOMM' that often. Now, he got his PhD from Cornell University in 2020, and he's now an assistant professor at Purdue University. His research interests are broadly in the area of data center networking and programmable networks. And I think this is also the topic of today's presentation. So Vishal, take it.
Thank you. Thank you, Anya, for the introduction. Hello, everyone. So this paper is, at a very high level, is about the hardware architecture of a programmable switch. So I thought that before I jump deep into the paper itself, it would be nice to just take a step back and look at how this hardware for programmable switches have evolved, say, over the last decade. Right? So ever since the RMT paper, the seminal paper, came out in SIGCOMM' 2013, our community has continuously tried to push the limits of what a programmable switch hardware could do. For example, in 2016, Domino was proposed that basically extended RMT with stateful operations. In the same year, PI4 was introduced, which basically introduced a push-in, first-out queuing primitive, using which you could do programmable packet scheduling on RMT switches. 3 years later, Flowblaze was introduced, using which you could do finite state machine operations on RMT switches. Later that year, PIO was introduced, which pushed the envelope for programmable packet scheduling with push-in extract-out primitive. And more recently, in fact, just a few months ago, in 2022, Taurus was proposed, which introduces a map-reduce primitive on the RMT programmable switches. So today, I'm going to make a case that we should have a new primitive for programmable switches, and that primitive should be multidimensional table filtering. And that's essentially is going to be the focus of this talk. So at this point, why multidimensional table filtering? What is so special about it? And the answer to that question is actually quite simple. We want this primitive because turns out it shows up at all over the places for many key in-network applications. For example, say you want to do a performance-aware routing, right? So for example, say you want to filter paths based on some performance metrics, and once you have those filtered paths, maybe you want to choose some path at random, right? That's one example. Maybe you want to do congestion-aware load balancing. You want to find a path, filter a path with minimum congestion, right? Or maybe you want to do something more fancy. You want to filter paths based on, or ports based on some variant of power of two choices, like a system called Drill does. Or maybe you want to do a resource-aware layer 4 load balancing. Maybe you want to do data plane diagnosis. Maybe you want to do policy compliance. And these are just the applications that I could fit on a single slide. So it is missing applications such as security and firewall, where also multidimensional filtering shows up all the time. Now, if you look closely at some of these applications or policies, you'll see that most of these policies don't just do one filtering operation. In fact, most of them kind of have multiple filter operations where you perform some filter operation, take the output of it, and perform another filter operation, and so on. For example, consider the first example, where we do a filter operation based on delay less than D and utilization less than U. You get some output, and then from that output, you do another filter operation and choose something at random. So the point I'm trying to make is that these are not just single filter operations, but these could very well be chains of filter operations. And finally, if you look at all these applications, most of them is what you would call quintessential data plane applications. So essentially, in the limit, you would want to run these applications at line rate. And what it essentially calls for is chain multidimensional filtering at line rate. Now, the next slide shouldn't come as a surprise that, well, we can't support this primitive on current programmable switches, even if you include all the extensions that I described in the first slide, you are still not able to do it, unfortunately. So with that in mind, I'm going to present to you Thanos. So those of you who are familiar with Marvel movies or Marvel comics know that this guy, Thanos, as soon as he got his Infinity Rings, he got this amazing power that he could filter out at random half of the population on like the entire universe and kill them basically, right, in just a snap of a finger. So it turns out we want something similar. Well, minus all the genocide, of course. So we want something similar in the sense that we also want to be able to perform these filter operations at a very fast rate. So metaphorically, in a snap of a finger, right? And the way Thanos achieves it is it introduces a new programmable filter module that sits in line with your traditional match action stages in your programmable switch. And this filter module has two key components. So the first component is obviously a multi-dimensional table. So this is where you will be storing all your relevant state. And then you have a filter processing pipeline that you could program with any custom policy. And then this pipeline would filter entries from this table at runtime based on that policy. So that's the high-level architecture. So next, what I'm going to do is I'm going to discuss what are the key filter abstractions and primitives Thanos provides. And finally, I will discuss the hardware design. So let's start with the abstractions and primitives. So one of the two basic primitives in Thanos is what we call Unary Filter Processing Unit, or UFPU. So UFPU takes as input a multidimensional table, and it returns a subset of that table based on the kind of filter operation that you want to perform. For example, you might want to perform a random operation, so this will just choose one of those entries from the table uniformly at random. Or you can do something more stateful, like, for example, you want to filter entries based on some predicate on some attribute. Or you could do something in a round-robin manner, or you could choose entries based on, say, max or min values of these attributes. So these are the 4 filtering operations that Thanos currently supports. And you might ask, right, like, why these 4, right? So it turns out there is nothing really fundamental that we only need to have these 4 operations. It just turns out that in our observation, these operations are sufficient to support most of the in-network applications that we have. And that's why we go with it. OK, so at this point, once you have this UFPU, you can start to get a little bit more ambitious. For example, you might want to have policies where you don't just want to filter one thing at random, but maybe filter n things at random, or have n least CPU-utilized load balancing servers from this table, right? So to do this, what Thanos does is it basically chains these UFPU blocks in a certain way, right? So for example, what you could do is you could feed your input into the first UFPU block, remove the output from the input, feed it to the next one, repeat it n times, and then you get what you get. And in the end, you just take the union of all those outputs, and that is your final output. So we abstract this entire thing, and we call it KUFPU. So KUFPU is just a generalization of UFPU, as it introduces a new configurable parameter called K, using which you can decide what should be the length of your chain. And so in our overall design, we actually use KUFPU as the basic computation unit as opposed to UFPU, just because it is more general. OK? So now it's time to get even more ambitious. So why just limit ourselves to unary filter operations? Why not do multidimensional filtering, right? So for example, you can have so that should have been KUFPU, but anyways. So you can have, say, 2 filter operations. You can take the outputs of those filter operations, and then you can perform a binary operation on top. And these operations could be like your typical set operations, like union, intersection, difference, and so on. So what can you do with this? So you can express a policy something like this, right? Filter all load balancing servers with available memory greater than X and available bandwidth greater than Y, and you can do that, right? And finally, you can just extend this chain to arbitrary lengths. For example, you can add another condition, that number of connections should be less than Z. You can take the entire output, choose M load balancing servers at random. You can get the output of it, choose the server with the minimum CPU utilization, and maybe this is your final thing that you are looking for. So this is how a typical filter chain in Thanos looks like. And we call it a serial chain filter pipeline. And this is an example of a 5-stage serial chain filter pipeline in Thanos. OK? So this is all about Thanos abstractions. So now, next, what I'm going to talk about is how do we take these abstractions and how do we build a hardware design for Thanos. So by now, you know that there are 2 key components here, right? So you have your multidimensional table, and you have your programmable filter pipeline. So what I'm going to discuss next is how we design both these 2 components. And I'm going to start with the multidimensional table. So the problem here is, pretty obvious, that we want to design an efficient data structure for a multidimensional relational table. And by efficient, we basically mean that it should allow line rate reads, writes, and updates on the table. So before I discuss our solution, let's see why the classical solutions are not good enough. So the filter operations that we are supporting, it's not new, right? Those filter operations have existed, forever. And there are many, traditional data structures that support those operations in a very efficient manner. It turns out there is no real universal data structure that can support all of those operations efficiently. So you have different data structures for different operations, unfortunately. And secondly, most of these data structures have a hierarchical structure, which is great if you are working on a CPU architecture. It can be proven to be optimal, and so on and so forth. But if you are building, say, a custom hardware where you have this opportunity to have a huge amount of spatial parallelism, this hierarchical structure actually becomes a kind of a bottleneck, and it doesn't allow you to reach line rate performance. So to get rid of these issues, we propose a new hardware data structure for multidimensional tables, and we call it Sorted Multidimensional Bidirectional Map, or SMBM. So how does SMBM work? So suppose you have this example table where you have an ID for the resource, and you have 2 metrics, x and y. So SMBM basically has 4 key properties. So the first property is that there is no hierarchy here. So we store all the dimensions as flat lists of flip-flops. So this basically allows parallel access and processing. Secondly, we store all these lists in a sorted order. So this is an invariant that the data structure always maintains. And the reason why we do that is because this would allow fast max and min filter operations. Thirdly, each of these dimensions are completely independent. So this allows you to do parallel operations on each of these dimensions. And finally, we maintain a bidirectional mapping between the IDs and the respective metrics. So the forward mapping basically helps you keep track of which attributes belong to which ID. And the reverse map comes in handy once you have filtered something based on some attribute, and you want to figure out which ID it belongs to. So you can do it very fast if you have this bidirectional mapping. So these are the 4 key properties of SMBM. And without going into the details, the SMBM Performance, you can read the entire data structure in parallel in 1 clock cycle, and add and delete operations can be issued every clock cycle with a latency of 2 cycles. OK, so next I'm going to talk about the design of the filter pipeline. So there are 2 key properties that you want out of this filter pipeline. So you want it to be fully reconfigurable. So what do we mean by that? Well, you should be able to express any arbitrary chain of filter operation with chain length less than equal to your number of stages on whatever number of input lines you have. And obviously, you want it to be fast, so run at line rate. So this is how the filter pipeline layout looks like. So it just has k stages, and each stage has n input lines and n output lines. So for reconfigurability, or full reconfigurability, it's easy to see that the sufficient condition is that you need to be able to basically apply any filter operation to any input or pair of input lines in each stage. And you should be able to connect that output of the filter operation to any of the output lines of that stage. And if every stage does that, then overall, you get full reconfigurability. The more details you can find in the paper. So if you try to actually do that in a naive manner, it's not actually that hard. right? You just have your, all the units, you have a crossbar, and that pretty much does it, to be honest. But the question, or rather the issue here is that the size of the crossbar is actually n times 2n. And this is because you have two different kinds of resources. And so in the worst case, what could happen is all the input lines might want to be connected to one kind of resource. And so to accommodate for that, you really need 2n lines, right? And this basically increases your crossbar size to n times 2n, whereas ideally, you really want to keep it to n times n. You can't do much better than that. So to do that, what we do is essentially we try to homogenize our basic units. So here, our basic units is heterogeneous. We basically rearrange them into what we call a cell. So this cell is homogeneous, and now you can see that you can connect these lines using just an n cross n crossbar. So how do we reconfigure this pipeline? So let me take a couple of examples, right? So suppose you want to apply a UFPU operation on input line 1 and connect it to output line 3. So the way you would do it is you would use the crossbar to connect it to the KFPU in the cell number 2. You will apply a no-op operation on your BFPU, and then that is already connected to the output line that you wanted to connect. If you wanted to, say, apply a BFPU operation, you will do a similar thing. You will again use your crossbar to connect it to the inputs of the right cell, and then apply no-op operations, this time on the KUFPUs instead of BFPU, and then you connect it to the right output. And once you have this ability, now when you have things in parallel where you want to do multiple filter operations at a time, what you can show is that you can always rearrange those connections in a way that the outputs of those filter operations can be connected to some permutation of the final output lines. Okay? So how does this filter pipeline perform? So the filter pipeline can process a new filter request every clock cycle. And it runs at clock speed in excess of 1 gigahertz. But all of this comes at a cost. And the cost is really scalability. And this is really a fundamental trade-off here. If you want line rate processing, you have to give up a little bit on scalability. And the bottleneck here is not really chip area or anything like that. The bottleneck here is actually clock rate. So as soon as you go beyond a few thousands of table entries, you are unable to hit 1 gigahertz clock rate, which is kind of our baseline to meet line rate for today's switches. But having said that, even though this scalability might look limited, it's still sufficient for many of the applications, because you have to consider what are these table entries about. So for most of these applications, these table entries are things like network paths, or switch ports, or servers in a cluster, and so on. For those applications, this much scalability is actually sufficient. But obviously, if you wanted to do something grandiose, for example, I don't know, you wanted to load balance client requests over hundreds of thousands of servers in a data center, clearly, one instance of Thanos is not going to be enough. So in that case, maybe you would want to explore multiple instances of Thanos, or maybe you would even want to explore multiple Thanos-capable switches, none of which we explore in this paper. So in terms of application performance, so here what I want to show you is that, well, we are trying to implement these rich filter policies, but do they actually give us any advantage in terms of performance, in terms of application performance? So here is one experiment that we ran. So the goal here is to basically load balance client requests over a bunch of load balancing servers. And typically, the way it's done today is, the servers are chosen uniformly at random, and client requests are sent to those servers, and they do the job. And this works pretty well most of the time. But let's suppose those load balancing servers are also running some other applications that might consume some amount of resources, right? Which was the case with the production cluster for which we ran these experiments. So in that case, it turns out that a resource-aware load balancing outperforms this random selection of servers by up to 1.7x to 1.3x. So the final thing that I wanted to highlight is, well, I have motivated Thanos so far completely in the context of networking applications. But if you think about it, multidimensional filtering is actually much more general than just network applications, right? There are many non-networking applications that use multidimensional filtering, and examples include, but are not limited to, online analytical processing, relational databases, multidimensional clustering in ML, and so on and so forth. So really, Thanos kind of paves a way to accelerate all of those applications by maybe offloading some or part of it in the network data plane. And to provide a proof of concept, we ran one such experiment where we tried to do an in-network caching of relational graph filter queries and see how much performance gain can we get. So essentially what we did was we looked at what are the most popular filter queries, and we implemented those filter queries in Thanos switch so that now most of these client requests don't have to go all the way to the server for response. So you save that RTT delay, plus you also save the processing at the server, because the processing at the switch is going to be much, much faster than the server. And overall, what it results is in 4x to 2.x better response time for all the filter queries that were cached. And those which are not cached obviously have to go to the server, and for that you don't see any performance gains. So to summarize, Thanos extends programmable switches with the ability to do programmable line rate filtering over a multi-dimensional table. Use cases, again, include performance-aware routing, load balancing, network diagnosis, security, firewall, so on and so forth. The design runs in excess of 1 gigahertz clock speed and scales to thousands of table entries. I already talked about the scalability limitation there. The evaluations show that you can actually gain some real improvements on real applications using this extension to programmable switch hardware. And overall, Thanos essentially just advances the current state of the art in network computing in two ways. It enables richer algorithms for existing in-network applications, and it also enables new in-network applications, example, caching of relational queries, and so on. Thank you.
Thank you very much. Are there any questions?
Yes, hello. Kamal Razai from TU Darmstadt. About the new data structure that you mentioned that it takes around 01 or for insertion and deletion, it takes 02. Can you elaborate that a bit more? Because I saw that you're using the sorted way of the data structure. How is that helping gaining that 01 cycle time?
Right, so the key there is that we store the data structure in flip-flops, right? So that is the double-edged sword, basically, because when you store it in flip-flops, you get this ability to do parallel processing, but it also limits your scalability, basically. So that was the point I was trying to make, right? So that's how you are able to do these things in constant time, because now you can do comparisons in parallel on all the entries in the.
Okay, so
but you also mentioned that you can do insertions in almost constant time.
Yes.
So how do you do that?
Yeah, so the insertion is pretty much similar, right? So for example, if you have a list, right? It's a flat list. It's a sorted flat list. And you want to enter something in that list at certain position, right? So basically what you need to do is you need to apply a priority encoder to figure out at what exact location it should go in, because it's a sorted list. So you have to insert it maintaining the invariant, right? So you first apply a priority encoder, figure out the location, and now you can utilize the fact that since it is in flip-flops, you can shift those entries all in parallel and put the entry in the right position.
But you also need to update all your reference pointers. How do you do that?
Yeah, so that's why we maintain bidirectional pointers, right? So that was one of the reasons why we maintained the bidirectional mapping. So the entry that you are putting in, you basically do the same operation on each of those dimensions in parallel, because like I said, they are all independent of one another. And once you have done it, you just update the mapping. So that's why it takes 2 cycles instead of 1.
Okay, thanks.
Thank you.
Hi, Jiaxi from Alibaba. So following that question, I actually have 2 questions regarding that. So first of all, how can you do insertions in 2 cycles without all those computations?
Without what?
So your insertion, how fast can it be performed?
2 clock cycles.
How the update is computed in 2 clock cycles without those mappings?
Without what?
So you can do it in line rate because you are, for example, you have a
No,
pipeline, right?
we can do it in line rate because it's pipeline. So latency is 2 clock cycles. but it is still pipeline. So if you read the paper, so in the paper I describe it, so the actual writing that happens, it happens in just one stage. So the first stage is you apply the priority encoder to figure out the location, right? So it is all pipeline, but the latency is 2 clock cycles.
Yeah, so then I assume, just to double check, I assume you can just, you have your filter, you have the input of the table. If you want to update the load, for example, for the load balancing examples, you want to upload the load, update the load of each server. So then what you can do is finish the computation and then go back to update the value, or how you're going to update the load.
Right, so the updating part is really not the part of the filter pipeline. So the job of the filter pipeline is to just filter things, right?
Yes.
So the update is happening in a certain different way. For example, it would depend upon what kind of updates you want to perform. For example, you said the example of load balancing server, right? So there you might have probe packets coming from that load balancing server, telling that, hey, this is my CPU utilization, so on and so forth. So there you would rely on the RMT pipeline to basically process those probe packets, and then it will be inserted into the table.
Thank you for your talk. It was really open-minding. You talked about the fact that you're doing application offloads, but for example, in load balancer, the path can be changed, right? So it might be that the data you have is stale, and therefore, how did you think about how to update the different load balancers you have around on your different Thanos instances, as that has to be very, very fast, else you actually overload the computer, right, the server.
Right, so here we're kind of assuming that the load balancing application would be installed on a Thanos switch, which is kind of central. So you can think of it as spine switches and so on, right? And then your question is that if the path changes, what happens?
Have you thought about how to do the updates? Because what will happen is that the information about the load balancing you will have on your instance might be different than the instance you have on a different Thanos instance.
Yeah, so that's where that brings back to the previous question. So the way I'm assuming that those updates would happen, because in this case, your resource is remote, right? So the way I'm assuming that those updates would happen is your resource would be sending some probe packets, right? So there, those probe packets, you will have to make sure that those probe packets go to all instances. Otherwise, yes, you will not have that synchrony across those instances.
Have you evaluated it? Because
no, in this evaluation, we assumed that you had one spine switch, and that's where everything was happening.
Thank you.
Yep.
Quick question, please.
Yeah, so my name is Boris Koldhofer, University of Groningen, and I was just wondering whether you see sort of from the multidimensional abstraction a similarity to content routing, and why I say that is because you mentioned that this is a completely new paradigm which cannot be implemented on TCAM memory. And if you think like content routing comprises really multiple attributes, filtering, and there is actually work which has shown that this is actually possible to be implemented on TCAM. Yeah. So I was wondering whether you see that completely different or whether you would I think your abstraction is really nice, but I think it's maybe a very strong claim to say that you cannot implement it on TCAM.
So I did not say you cannot implement it on TCAM. What I said is that it's hard to implement both the filter pipeline and the way you store those multidimensional tables on our current programmable switches. So that's slightly different.
Okay, the rest you take offline. Quick question.
Okay, thanks. How can you ensure connection consistency? Because your use case is load balancing, and weighted round robin and random, we can already do that on a Tofino chip. So how then you ensure that all packets of the TCP flows go to the server you actually selected?
So that is very much a complementary problem, right? So that really is what state you are storing in your switch, right? So this is the way in which you figure out what server to map to, right? And once you have figured that out, you can cache it in your switch in some other table, which solutions like Silk Road already do, and then all the subsequent packets that belong to that flow will basically bypass this filter operation, directly go to that table, see what the mapping is, and go to that server.
Okay, that is a good segment into the next presentation. But before we do that, one more question from me, and that is, what is the price of the flexibility that you're introducing here?
What is the?
What is the price in terms of architectural space, power hungriness, etc.?
Right. So what we saw was, at least for the kind of scales that we are talking about here, like few thousands of entries, chip area was really not the bottleneck, like I said. It's the clock speed that becomes kind of bottleneck. So if you're thinking in terms of chip area overhead or power overhead, it's really not that large. Obviously, if you increase to the higher scale, then it would become an issue.